last video we went through a breakdown of how to find the eigenvalues and vectors of the following matrix. Okay, and we said that basically you look at the following matrix by subtracting the diagonals by the eigenvalues, and we had found that one eigenvalue was -1 and one eigenvalue was 5. And I showed you how to find the eigenvector, at least associated with 5. You design the system of equations by plugging in the 5 there. 3 minus 5, 0, 0, which equates to solving the system -4, 2, 4, and -2. Which we mentioned that that's the same as -4 times x1 plus 2 times x2 is equal to 0. And we basically said if we were to let x2 equals t, then basically what we get is x1 is equal to 1/2 of t, and x2 is equal to t. And the eigenvector was therefore 1/2 and 1. If we had done this with the other eigenvector, minus 1, 4, 2, and 3 minus 1, 0, 0, we would have gotten 2, 2, 4, and 4, 0, 0 on both ends, which equates to basically just x1 plus x2 is equal to 0. x2 is equal to t, same deal. T is just an arbitrary number. I'm just saying let x2 be anything. Why are we doing this? Because the bottom row disappears, and when we multiply this by the x1 and x2, the x2 disappears because of the zeros on the bottom here. And so we're only left with an expression for this one. So typically what we do is we just say set the second one, and sometimes even third or fourth, fifth, however many we have. These are what are referred to as free variables, by the way. They're free because they don't have an explicit solution. We can set them to anything we want to. So we just say let it be set equal to t, in which case we have x1 is equal to minus t with x2 set equal to t, which means we're left with the eigenvector -1 and 1. So what's interesting about this is that you can actually construct a matrix of the eigenvalues. So here we have the matrix 1/2, 1, -1 and 1. And what's very, very interesting about this is that you can actually write the matrix in terms of the eigenvalues and the eigenvectors. The first step is obviously to find the eigenvectors, which we had done in the prior videos. The second step is to find the eigenvectors and then create a matrix of those vectors. The next step is to find what's called the inverse of the matrix. And I haven't really gone through how to find this because, frankly, I don't care. Computers usually do this for us, but if you wanted to do this by hand, one approach to finding the inverse of a matrix is to do a bar and set it equal to the identity matrix on the other side. And then what you do is you go about doing Gauss-Jordan elimination. So this converts to multiply 2 across the board. You get 2 minus 1, 2 and 0, 1, 1, 0, 1. You can then, actually, I'm going to start here all the way on the left so that there's some room here. So starting from this point, what you can then do is, I'm sorry, that's not 2. 2 times 1/2 is 1. Minus 2 times 2 is minus 1 times 2 is -2. Then you get 2 here and here. I'm sorry, I know some of you are probably like, what are you doing? Anyway, we have 1 minus 2, 2 and 0. Getting rid of the 1 using Gauss-Jordan elimination, we just do -1 and then we multiply the whole row by -1 and then add. So this goes to 0, this goes to 3, this goes to -2, and this goes to 1. Divide the bottom row by 3 to get -2/3 and positive 1/3 to 0. And then last, do the same thing to get rid of the, to emphasize this, do the multiply by 2 and add, and to change the top row. So multiply the bottom row by 2 and then add the result to the top row. So we have just 1, 0, not -2, I'm sorry, positive 2. Here we get 4/3. So we get 2 minus 4/3. And here we get just 2/3 with -2/3 and 1/3. And you'll notice that on the left-hand side, we now have the identity matrix, and on the right-hand side, we have a different matrix, which that resulting matrix is the inverse of this original matrix. So cleaning some of that up, we have found that the resulting matrix, multiply top and bottom by 3 minus 4, that's 6 minus 4, 2/3, 2/3, minus 2/3, and 1/3. And you can double check that. So same business that I'm going to do here as I've done in past videos, just delete all this mess. And what you can do to test if that's actually the inverse, multiply the two matrices together. So here we have 2/3, 2/3, minus 2/3, and 1/3. So let's see what we get here. For the first entry, this times this plus this times this. So what do we get? 1/2 times 2/3 is the same thing as 1/3, and the plus 1 times 2/3. So we get 1/3 plus 2/3, which is 3/3. So we get 1 in the first entry here. Second entry, we multiply this times this. 2/3 times 1/2 times 2/3 is the same thing as 1/3. And then minus 1 times 1/3 is minus 1/3, which of course we get 0. 1 times 2/3 minus 2/3 is 0. And 2/3 plus 1/3 is 1. So as you can see, when we multiply these two, if you remember, this is the matrix C and this is the matrix C inverse, we get the identity. So this is indeed the inverse of that matrix. Now, here's what the interesting part about all of this is. The interesting part about all of this is that if we have a square matrix A that has eigenvalues, positive or negative eigenvalues, but non-zero, then we can actually write the original matrix in terms of the multiplication of the following: the eigenvector matrix times a diagonal matrix with the eigenvalues associated with each eigenvector. So remember, this is the eigenvector associated with the eigenvector 5. This is the eigenvector associated with the eigenvalue minus 1. If we write the inverse of that matrix on the right-hand side, okay, we should get back the original matrix A. Put differently, I was able to do what's called decompose the matrix A into a multiplication of the matrix of the eigenvectors the matrix of the diagonal matrix of the eigenvalues and the inverse matrix of the eigenvectors. Let's see if that holds true. This times this is 5 over 2 plus 0. This plus this is 0. Minus 1 is positive 1. This times this is 5 plus 0. And then we have this times this is 0 plus this times this, which is minus 1. So for the first two, we get this times 2/3, 2/3, minus 2/3, and 1/3. Now let's carry out that multiplication. 5 seconds times 2/3 is 5/3. Minus the 2/3, because this times this, right? Minus the 2/3. Second one, 5 seconds times 2/3 is 5/3, plus 1/3. The next one is 5 times 2, which is 10/3, plus, minus and minus cancel, plus the 2/3. And then we get 5 times 2, which is 10/3, minus the 1/3. And if you look through this, we get 5 minus the 2, which gives us 3/3, which is just 1. 5 plus 1 is 6 over 3, which is 2. 10 plus 2 is 12 over 3, which is 4. And 10 minus 1 is 9 over 3, which is 3, which magically you can see was the original matrix indeed. So what have we illustrated here? We have illustrated the idea that for a square matrix A, if all of the eigenvalues are not equal to 0, then I can decompose A as a multiplication. Okay, I'm going to bold this. As a multiplication of C of the matrix of vectors. The inverse of eigenvectors, and last, the diagonal matrix of eigenvalues, where each value in the diagonal corresponds to the column that is in the corresponding eigenvector. We will see in a few moments that this decomposition will help us calculate very complicated things very, very quickly.